Welcome to the video. Today we will explore in this video a fascinating topic in particle physics. The topic is Quark-Gluon Plasma. In short, this is known as QGP, and there is one question to be discussed. In this video, the question is why free quarks or gluons are impossible. So this is the topic of discussion in this video. So Quark-Gluon Plasma or QGP, this phase of matter existed. This is an exotic state of matter, and this phase existed just after the Big Bang. The time gap was only 10 microseconds, approximately 10 microseconds. And when the universe cooled down, there was a change in the state. When it was in the plasma state, means which is known as Quark-Gluon Plasma, in that state, that state is known as a deconfined state. And when the universe cooled down, the new state was formed, and that new state is known as confined state. So there is a difference between deconfined state and confined state. But actually what happens, and this thing has already been experimentally verified in Large Hadron Collider, that is known as a LHC, Large Hadron Collider, and RHIC, Relativistic Heavy Ion Collider. What is the difference between these two states, deconfined state and confined state? In both the states of Quark-Gluon Plasma, the quarks, quarks and gluons. Quarks are what? These are the constituents by which neutrons, protons, and other hadrons are formed. So these are the constituents of hadrons, quarks. And gluons are what? These are mediators of force. Which force? Strong force. Mediators of strong force. Those are gluons. Okay. But the problem is what? In the deconfined state, means in the early universe, they were in the deconfined state, means the plasma state, that is known as the deconfined state. In that case also, the quarks were not free. Somehow they were bound together. They cannot be treated as free, and in ordinary conditions also same thing happens. They are not free. They cannot be made free. Okay. So what is the actual reason behind this? What is the cause behind this? Why they cannot be made free? I'm talking about both quarks and gluons. So suppose you take two quarks, Q1 and Q2, small q1 and small q2, two quarks you take. And if you make an attempt to pull them apart, what happens actually? If you try to pull them apart, the strong force between them increases, and it increases dramatically. Unlike the electromagnetic force, what happens in case of electromagnetic force? When the objects are taken away from each other, the electromagnetic force weakens. But here in this case of quarks, if you take them apart, the strong force grows, and it grows dramatically. That means it increases, just like a rubber band. If you take one rubber band and if you try to pull them apart, means if you apply a tensile force in the rubber band, what happens? The force increases. As it lengthens, the force increases. Similarly, here also, when quarks are taken apart from one another, so in that case, the strong force grows or increases. And at a point, the energy increases. Okay, so at a point, the energy manifests itself by the formation of a new quark-antiquark pair. This formation of quark-antiquark pair occurs from vacuum, but there is a formation. Okay, the increased energy manifests itself in this way, but you cannot pull them apart, you cannot make them free. So this phenomenon occurs when you are making an attempt to separate the quarks. So I was talking about two quarks. If you take two quarks, suppose Q1 and Q2, and suppose when energy manifests itself by the formation of a new quark-antiquark pair, suppose they are denoted by Q3, small q3, and small q4a, small a for antimatter, means antiquark. Q4a stands for antiquark, new antiquark, which has been formed. Okay. Now, so what happens? Then again they combine to form two meson particles, but both the meson particles are not same. Suppose I am talking about meson 1, where first you have taken two quarks Q1 and Q2. Suppose you are taking Q1. So Q1 combines with Q3. Q3 is what? It is quark. So Q1 combines with Q3 to form a new quark. Q1 and Q3. So Q1 plus Q3. Okay. It's a new meson, not quark, sorry. It's a new meson known as meson 1. And there was one more quark known as Q2, denoted by Q2. So Q2 plus Q3, Q4a. Q2 plus Q4a, this makes another meson known as, denoted by meson 2. So you can see that meson 1, in meson 1 what is there? In meson 1, Q1 is there and Q3 is there, and both are what? Both are quarks. But in meson 2, what are there? In meson 2, Q2 is there, Q2 is nothing but quark, and Q4a is there, which is actually antiquark. So you can see that both the mesons are not same, meson 1 and meson 2. So in both the confined state and deconfined state, always you will get that they are not free. In confined state they are not free. Again in deconfined state they are not free. Yes, in case of deconfined state occurs when? I was talking about the early universe, where the temperature was extremely high. Temperature was in terms of the temperatures were in terms of you can say trillions degrees Kelvin. And in the experiment also, in case of a Large Hadron Collider or relativistic heavy ion collider, in that case also that temperature is generated trillions of degrees Kelvin. Trillions means 10 to the power 12. In LHC, the recorded value is, highest recorded value is 5.5 trillion degrees Kelvin. That is the recorded value, that is the highest temperature achieved at LHC. So only at this temperature you can see the Quark-Gluon Plasma state. Plasma, this is a state of matter. But when it cools down, so in that case energy is also very high. So now you can easily see the reason behind, you can easily understand the reason behind the fact that why they cannot be separated, why the quarks cannot be separated. And similar analogy is applicable for gluons also. Okay, similar analogy. If you compare gluons with photons, then you can see that photons, that is the cause behind those electromagnetic forces, and they are neutral. But in case of gluons, they are means color concept is there, means they carry color charge. Quarks also carry color charge. like red, blue and green. And in case of gluons also same thing is there. Anyway, I am not talking about here right now color charges. Okay, so what is the implication of this study of QGP? You know that in the early universe, matter evolved during the Big Bang. So to focus on that thing, we need to study QGP, this phase of matter, which is known as exotic state of matter. Again, in particle physics, there is one concept known as quantum chromodynamics. So to test the theories of quantum chromodynamics, this study is necessary. Again, to study deeply the neutron stars, then black holes, then other high energy objects, okay, the study of QGP is necessary. Anyway, so this was all about today's topic, QGP and why quarks and why free quarks and gluons are impossible. Okay, so this was the topic of discussion in today's lecture. In a separate video, I'll discuss about those color charges. Okay, color charges of quarks. Anyway, so this was all about today's topic, today's video. So this is the end of this video. Thank you for watching this video.